Hello there, and welcome back to the Sleepy Science. You're lying still now, but everything around you is shifting, leaning, wobbling just a little out of line. If you squint hard enough, no, softer, you might catch it. The outline of your bookshelf maybe, or that phone screen you swore was flat. But give it time, let your gaze blur, and you'll start to notice the truth. The universe really doesn't do straight lines, not well, not naturally, not often. In fact, the deeper you look, the more you'll see curves, kinks, ripples, folds. From the edge of your pillow to the farthest rim of space, everything bends. Even your thoughts spiral a little, especially at this hour. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments, where in the world are you listening from, and what time is it for you? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're lying on your back, the universe overhead, and it feels oddly personal, like it's watching you back. But don't worry, it's not malicious. It just disagrees with rulers. Try drawing a line across the sky. Go ahead, imagine it. One crisp Euclidean stripe from one star to the next. There, you did it, except no, you didn't. Because the moment you tried to go straight, you were tricked. That line, it bent. It had to. Space itself curved beneath your imaginary chalk, and gravity pulled at its edges like a toddler yanking a tablecloth. You drew a circle without knowing it, or more precisely, a geodesic. The universe's idea of straight is already warped from the get-go. You're not alone in falling for the illusion. For most of human history, people believed the world was flat and the stars sat fixed in nice, neat rows. Euclid and his pals laid down some pretty sturdy geometry back in 300 BCE, and for a long time, that was the gospel of lines. Parallel ones, even ones, clean ones. Historians still argue whether ancient Egyptian architects used true right angles or simply eyeballed their pyramids. But either way, those sharp edges were a human desire, not a natural one. Meanwhile, look outside. Find a tree. The trunk might seem straight at a glance, but zoom in, and it's a mess. Little bulges from old knots, micro-twists in the bark, maybe a lean toward the sun or away from last winter's wind. Every so-called straight tree is just a lumpy cylinder doing its best. Gravity and biology twist it slowly over time, like taffy pulled in slow motion. Now you're in a forest in your mind, barefoot of course, and you're walking between trees that never grow in rows. You push past brambles that wrap, roots that tangle, branches that arch overhead like nature's own Art Deco chaos. Nothing about this feels straight, and that's because nature prefers adaptability to symmetry. Straightness is fragile. One gust of wind, one raindrop, and the perfect line becomes a perfect mess. Take the horizon. It looks flat, right? But no. Not only is Earth a sphere, she's not even a particularly round one. Earth bulges at the equator like someone who's had one too many donuts, and this oblate spheroid shape means that even our most beloved illusion of flatness, the sea level horizon, is just a curved line from a particular angle. Move, and it moves too. You never see a truly straight horizon unless you Photoshop it. Speaking of illusions, let's hop into your brain for a second. It turns out you're kind of obsessed with lines. Your visual system is wired to detect edges. Your survival depended on spotting a straight spear coming at you or the straight edge of a cliff. But the trade-off is that your brain invents straightness where it doesn't exist. You see lines in constellations, in sidewalk cracks, in the folds of your bedsheets. They're not there, or at least not quite. There's a curious phenomenon called the Canessa triangle, where your mind sees a triangle that isn't drawn, just suggested by other shapes. The triangle appears crisp, defined, almost glowing, but there's no line. Your brain hates that ambiguity, so it draws one for you. That's how far we'll go to cling to straightness. We hallucinate it. And yet, the universe remains unimpressed. Even light, the fastest, straightest thing we know, refuses to play by Euclid's rules. When light passes near a massive object like a star or black hole, it bends. Not because the light decided to take a shortcut, but because the space itself is warped. Einstein showed us that mass curves spacetime, and light is just following the new shape of reality. It's like walking across a trampoline with a bowling ball in the middle. You can't walk straight because the surface curves under your feet. We didn't always know this. In 1919, during a solar eclipse, Sir Arthur Eddington snapped photos of starlight bending around the sun. It was the first time humans caught the universe in the act of breaking straight lines. The press lost their minds. Light bends. Einstein was right. It made headlines across the world. And yet today, most people barely think about the fact that every ray of sunshine you feel on your skin had to curve a little to reach you. So here you are now, curled up and comfy, listening to stories about why straight lines are kind of a lie. But that doesn't mean they're useless. We need lines to make sense of things, to build, to plan, to not go totally bonkers when we're assembling IKEA furniture. But in the big picture, in the ancient galactic fundamental sense, those lines, they're illusions of control. The universe doesn't hate straight lines because it's malicious. It's just honest. It prefers motion, wiggle, fold, complexity. What you call mess is just the deeper truth. So go ahead and draw your neat little line. The stars will wait, and then gently curve it when you're not looking. You think you're pretty good at seeing straight lines? Look around your room right now, or better yet, just imagine it from under your blanket where it's safe and warm. The edge of your desk, the seam of the wall, that perfectly rectangular phone screen glowing on your nightstand, they all look straight, flat, reliable. But here's the thing, your eyes are lying to you, constantly, and your brain is in on it. The human visual system is brilliant, but also a little bit desperate. It evolved in a curvy, chaotic world and decided to fight back by pretending it saw order. Your mind smooths out wrinkles, aligns misaligned edges, and fills in gaps because it craves predictability. But sometimes, it smooths things so much it forgets reality was never clean in the first place. This illusion is called perceptual straightness. Your brain assumes things are straight unless they're clearly not. Take the cafe wall illusion. When you see a series of staggered black and white bricks, your brain insists the lines between them are slanted, even when they're dead straight. That's your visual cortex trying to interpret contrast as geometry and failing adorably. But that's just the start of the visual betrayal. Look up into the night sky again. Stars appear to sit on a flat dome. Ancient astronomers swore by it. They imagined celestial spheres, concentric crystal shells with stars glued on, and for a while that worked. But in reality, those stars are flung across a vast, three-dimensional mess of space. Some are just a few light years away, others are thousands. There's no plain or tidy wall up there. You're seeing 2 dimensions when there are really 3, or 4, depending how you count time. Historians still argue whether early astronomers genuinely believed in a literal firmament, or if it was just a mathematical convenience. Either way, it proves the same point. When your eyes see depthless perfection, they're probably faking it. The Romans, for example, adored their straight roads and orderly cities, but even they knew the world wasn't actually flat. So when they built a straight road, they were really laying a segmented curve that approximated a line. Roman surveyors used a device called a groma, a cross-shaped tool to align visual markers. But hills, rivers, and wobbly human judgment meant that most Roman roads snaked just slightly, gracefully, across the land. And yes, the Romans also had those famously straight aqueducts, but look closer, literally, go zoom in on one online. You'll find gentle gradients, bends around hills, and adjustments for terrain. True straightness was never the point. Function was. Meanwhile, your brain still clings to the illusion. In fact, you're wired to trust straightness so much that entire fields of design rely on exploiting it. Graphic designers, for instance, use what's called alignment bias. If the elements in an image almost align, your brain will fudge it and assume they do. It's part of why some logos feel satisfying without you ever realizing why. You're not detecting actual order, you're hallucinating it. And that brings us to the phenomenon of pareidolia, your delightful tendency to see patterns where none exist, faces in clouds, animals in toast, lines in chaos. That's your brain squinting at the world and saying, okay, let's pretend. It's charming, sure, but it also means that when you think you're perceiving something solid and linear, you might actually be navigating a dream your cortex invented 5 milliseconds ago. Now float with me into the desert. No, not metaphorically. You're in a mirage now, those shimmering pools of water that never appear where you want them to. What you're seeing is light bending, thanks to layers of hot air near the ground. It's called refraction, and it bends the light rays so they appear to travel in a curve. Your eyes assume those rays came straight because that's their default. So your brain paints a fake puddle to make sense of the distortion. Even your glasses, if you wear them, are tricking you right now. They bend incoming light to correct your vision, and your brain reprocesses that data without telling you anything's changed. That entire corrective process feels invisible, and yet it's built on optical lies. There's a reason lenses are curved, to fix the curves inside your eyes. Here's a weirder one, the moon illusion. Have you noticed how the moon looks massive near the horizon but tiny overhead? It's not actually changing size. Your brain is just comparing it to nearby objects, buildings, trees, telephone poles, and interpreting the distance incorrectly. It tries to force a perspective onto something that defies linear logic. And it gets worse. Optical illusions like the Mueller-Lyer illusion, those little arrow shapes, fool even trained neuroscientists. Show someone two lines with different end caps and they'll swear one's longer. It is. But again, your brain cheats, adding helpful context that warps perception. You are a beautiful, pattern-seeking liar, and you can't stop. Even shadows get in on the game. In some lighting conditions, a perfectly flat surface can appear bowed or bulged, simply because your brain doesn't process gradients perfectly. It's always guessing at lighting direction and object depth. That means that straight pencil on your desk might look warped when a sunset slants through your window. You're not losing your mind, it's just how vision works. Want to take it further? Step into an old funhouse. Remember those warped mirrors? There's something oddly satisfying about seeing yourself stretch, bend, squish. Because in some part of your mind you know the real shape, but you see the lie. That disconnect is funny, but it's also your everyday life. You're constantly reconciling what you know versus what you perceive. Even in digital environments, developers simulate perspective by faking straight lines that curve with camera distortion. In 3D rendering, the closer an object gets to the edge of the screen, the more its straight edges warp due to projection. Video games and animated movies hide these bends with subtle camera tricks because our eyes are not great at parsing real geometry. It's all lies, helpful lies, comforting lies, the kind you don't notice until you stop and look at them too long, but they add up to something meaningful. Your brain has no business insisting that the world is straight. The world is. Your brain just likes it that way. So as you drift deeper into this sleepy spiral of half-truths and crooked lines, remember, what you see isn't always what you get. It's a negotiation between chaos and clarity. And your brain, it's a surprisingly willing accomplice in the whole beautiful deception. You're walking now, slowly, lazily, as if each footstep could melt back into the one before it. And even though you're not going anywhere, your body still insists on motion. You place one foot forward, then the other. And if you imagine it just right, you're tracing a line, maybe across a hallway or through a field or along the quiet aisle of a nighttime grocery store. But surprise, surprise, that line, not straight. Human walking is a strange, squishy business. From the outside, it looks rhythmic, maybe even mechanical. One leg swings, the other supports. Repeat, but zoom in. Trace the actual path of your belly button as you walk, not that you've ever tried. And really, don't try to do this in public, people will stare. But imagine it now in your mind's sleepy eye. That path draws a gentle sine wave. Up, down, side to side, tiny undulations because your hips rotate, your knees bend. Your feet push off at slightly different angles every time. Biomechanists even have a name for it, the inverted pendulum model. You walk by vaulting over your planted leg like a one-legged pirate on a pogo stick. That's not just inefficient, it's downright wobbly. But it works. You're a soft, lumpy organism designed for squishy terrain, not hard-edged paths. Every straight line you walk is a wobble-filled suggestion. And here's the kicker. If you try to walk in a perfectly straight line with your eyes closed, you'll fail. Every time. You'll veer, usually to your dominant side, and spiral without even knowing it. This isn't just anecdotal, it's been tested again and again. In one study, blindfolded participants were told to walk straight through a field. Without visual cues, they wandered in slow, unpredictable circles like confused Roombas. Turns out, proprioception, the sense of where your limbs are, can't compensate for your total lack of external reference. Your inner ear lies too. A little to the left, a little more, and suddenly you're retracing your own footsteps like a forgetful ghost. Historians still argue whether early explorers navigated long distances using pure dead reckoning, or whether they relied more heavily on environmental cues like stars, wind, or migrating birds. But one thing is clear: if you took away their tools, they'd drift, just like you, just like everyone. And then there's terrain. Try walking straight through a forest. Go ahead. Every tree you detour around shifts your path. Every route you step over alters your angle by a degree or two. Add wind, slope, mud, or the irresistible lure of a mushroom, and your straight line becomes a chaotic doodle. Even animals can't walk straight without help. Watch a dog off-leash at a park. Unless it's fixated on a squirrel, it zigs and zags, sniffs and loops, investigating every scent-based whisper in the dirt. Birds in flight rarely fly a dead straight line. Wind and instinct constantly correct their course. Ants, they follow pheromone trails that bend, split, and swirl like chemical calligraphy. Straightness is a privilege of maps, not of movement. And what about those fancy human attempts to impose order? Airport runways, train tracks, marching bands. Surely someone gets it right. Sort of, but even there, the illusion frays at the edges. Train tracks, for example, often look dead straight, especially over long distances. But in reality, they're subtly curved to adjust for terrain, thermal expansion, and structural stress. Lay them truly straight and you invite disaster. Steel expands in heat, contracts in cold. Too rigid a structure snaps, buckles, or derails. Civil engineers learned that the hard way. Runways, too, are rarely as straight as they seem. Many are built with slight arcs to follow the Earth's surface, or to manage crosswinds and noise patterns. What looks straight on the ground might trace a curve when viewed from above, like a lie told politely. And marching bands. Even in precision military parades, the alignment is mostly a trick of synchronization. Watch from overhead and you'll spot microcorrections. Left footers edging wide, right footers crimping in, each person wobbling just slightly. That straight formation is a choreography of constant correction, not natural symmetry. This brings us to the peculiar field of locomotor ergonomics, the study of how humans move efficiently through space. Turns out we're designed to be lazy, not in a bad way, in an elegant, physics-loving way. Our joints and muscles favor motion paths that save energy. And guess what? Those aren't straight lines. They're arcs, spirals, slight figure eights. Consider your arm as you reach for a cup. You don't move it in a rigid line. Your elbow bends in, your wrist adjusts, your fingers curl, all in a fluid, swooping pattern. It's faster, it's smoother. It makes your cup of tea less likely to end up on your lap. Even your heartbeat, a marvel of rhythmic precision, moves blood in looping patterns, not straight shots. Arteries curve, veins meander, capillaries twist through tissue like overcooked spaghetti. All for a reason. Curves reduce pressure. Reduce wear. Straight lines in your circulatory system would kill you faster than a bad salad. And speaking of loops, your inner ear, the vestibular system, uses tiny curved canals filled with fluid to track your orientation. Those semicircular canals don't just look cool, they are cool. They detect rotation, tilt, and movement in 3 dimensions. Without them, you'd fall over every time you blink too hard. Curves keep you upright, curves keep you going, curves are you. So the next time you tell yourself you're heading in a straight line, physically or metaphorically, remember your inner wobble, the hips that swing, the toes that overcorrect. The trail you leave behind that, if traced, looks more like a gentle meander than a purposeful sprint. The universe isn't trying to mess with you. It just prefers its motion a little jazzy, a little off-center, and deep down, so do you. You're standing at the edge of something now. Maybe a road, a long, supposedly straight one. The kind that slices across the horizon like it means business. Maybe it's an empty desert highway under a salmon-pink dusk, or an old Roman road whispering through English countryside, cobbled and worn, lined with sheep who couldn't care less about geometry. From here it looks linear, confident, but you've been here long enough to know that's a lie too. Because the Earth, for all its comforting bulk and bedtime blue, is a sphere. Well, not even that. It's an oblate spheroid, which is science's fancy way of saying it's a little pudgy around the equator, a planetary dad bod. So every line you try to draw on its surface is inherently curved. No exceptions. Still, humans love their straight roads. They feel powerful, clean, efficient. Early civilizations got absolutely giddy about lining things up with stars, solstices, or their own egos. And the Romans, oh, they practically invented the flex. Roman roads were built with this reputation for unflinching straightness. They stretched for miles and miles, cutting through forests, mountains, and inconvenient local villages. And while they seemed straight, Roman engineers weren't foolish enough to deny the Earth's roundness. They used a technique called chord surveying. Instead of trying to follow the curve of the Earth or forcing a perfect line across undulating terrain, they laid out a series of straight segments, each short enough that the curve beneath them didn't matter much. Then they connected those segments with minor adjustments. The result? Something close enough to a line that, to the average sandaled legionnaire, felt satisfyingly infinite. Historians still argue whether they did this for ideological reasons. Rome conquers the land this decisively, or for practical ones like draining water efficiently. Either way, the effect was the same: roads that defied the land, or pretended to. Fast forward a few centuries and we're still at it. Highways in the American Midwest, especially, seem to run ruler straight across the plains. But look closer, zoom out, and you'll see the curvature creep back in. Road engineers use geodesic calculations now, which means they account for the Earth's roundness when plotting long distances. What looks straight on your windshield is really a shallow arc conforming to a much larger sphere. In fact, airplane routes, those curved lines you see on flight maps, aren't detours. They're the shortest path between 2 points on a sphere, called a great circle. If you've ever wondered why a flight from San Francisco to Tokyo seems to loop weirdly northward, that's not the pilot showing off. It's geometry doing what geometry does when space is bent. And here's a neat twist. When we build things flat, they often rebel later. Take long bridges. Engineers must account for the fact that Earth is curving away beneath them. A perfectly flat bridge would, paradoxically, dip below the Earth's surface if extended too far. So long-span bridges like the Verrazano Narrows in New York are subtly arched, not just for strength, but to match the shape of the world. The difference between the center and the ends can be several feet. You'd never notice. But the math knows. The math always knows. Then there's GPS. Oh yes, your phone right now thinks it's plotting you on a tidy little 2D map. But behind the scenes, it's accounting for a lumpy, rotating planet with gravitational anomalies, tectonic drift, and something called the geoid, which is like the Earth's real shape if you stripped away oceans and politeness. It's not pretty, but it's honest. That's why your GPS sometimes jumps as you drive. It's not you, it's spacetime refusing to sit still. Now let's talk tunnels. You think digging underground would offer a rare chance to go actually straight, right? No terrain to dodge, just go forward. Except no. The tunnel under the English Channel, is a marvel of engineering. But even that had to curve subtly, not just for geological reasons, but to accommodate Earth's rotation, pressure gradients, and tidal shifts in the rock. Engineers from England and France started digging from opposite sides. And yes, They met almost perfectly, but only because they constantly adjusted for tiny bends, long before the dirt was ever disturbed. Even satellites can't orbit in a straight line. They follow elliptical paths, bending constantly around the Earth. That's just what gravity does. It bends everything toward mass. If you want to stay still relative to a point on Earth, like for a communications satellite, you have to orbit at just the right height and speed, a geosynchronous dance on a curved stage. Any straighter and you'd fall. So when you trace your finger across a map and dream of straight paths, across continents, across oceans, you're flirting with fantasy. The Earth doesn't allow for straight, not on her surface, not above her, not below. Now imagine building a perfectly straight skyscraper. Easy, right? Up is just the opposite of down. Except it is. Up in New York is a slightly different direction than up in Dubai or Buenos Aires, because up is local. It's the line perpendicular to the ground beneath you, which itself is curved. So a building in Chicago is technically leaning away, just microscopically, from one in Tokyo. If you extended two perfectly vertical skyscrapers far enough into space, their tops would never meet. They diverge, just like your morning thoughts and your afternoon decisions. Straight, as it turns out, is always relative. There's a lovely anecdote floating around engineering circles. If you built a long enough straight railroad track with rails laid perfectly parallel and flat, and you ignored Earth's curvature, the train would eventually derail because the track would start floating above the ground. Absurd, maybe, but the point stands. Even steel can't escape geometry. So next time you're on a plane or driving a road that seems like it'll never end, remember, every apparent line is a compromise, a negotiation between human stubbornness and planetary truth. And as you settle into that realization, feeling the tilt of the Earth under your imaginary feet, you might find comfort in the bend, in the idea that nothing ever really goes straight, but everything still finds its way forward. Just like you. Now let's float upward just a bit off the ground, away from all that wobbly walking and those pseudo-straight roads. You're not flying exactly, more like hovering, light as a soap bubble, because you need some perspective to understand what might be the universe's greatest straight-line enemy, gravity. It doesn't punch, it doesn't yell, it just pulls, relentlessly, softly, and it bends everything it touches. You'd think light, of all things, would escape this fate. After all, it's fast, like record-breakingly fast. But no, gravity got to it too. Light may travel at 299,792 kilometers per second, but it still listens when gravity whispers. Einstein told us so. His theory of general relativity changed everything by suggesting that gravity isn't a force pulling things down, but rather the warping of spacetime itself. And once spacetime bends, anything traveling through it, light, a rock, your dreams of a straight life, has no choice but to follow the curve. Imagine rolling a marble across a trampoline. Now put a bowling ball in the center. The marble no longer rolls straight. It curves inward. That's how planets orbit stars. Not because the star is pulling with some invisible string, but because the planet is simply rolling along a curve in spacetime created by the star's mass. That same curvature bends light, too. In 1919, as you might remember from your half-awake dreams in Section 1, Sir Arthur Eddington photographed stars during a solar eclipse and found that their light had curved ever so slightly around the sun. It was the first visual proof that Einstein's wild idea was right. Even the straightest thing we know doesn't move in a line. Historians still argue whether Newton would have ever come around to this idea had he lived long enough, or if he would have just furrowed his brow, whispered witchcraft, and retreated to his apple trees. Either way, Einstein's theory knocked straight-line motion off its throne for good. Let's think about that light again. A photon fired from a distant star, hurtling through the void, minding its own business, then whoosh. It passes near a galaxy cluster and gets its trajectory bent, like a drunk taking a corner too fast. This is called gravitational lensing, and we've captured it on camera. Giant masses, like black holes or clusters of galaxies, literally bend background light into arcs and rings. They can even produce what scientists cheekily call an Einstein ring, a full circle of light formed by bending a galaxy's image around a nearer object. You may have seen one of these images without knowing what it was, a blurry swirl like a cosmic donut, but that's just light obeying gravity's gentle push. And gravity's power doesn't stop there. It bends time too. Clocks tick differently depending on how close they are to a massive object. That's why GPS satellites, hovering up there in orbit, need constant time corrections. Their clocks run just a tiny bit faster than ours on Earth. Not by much, nanoseconds, but enough that your directions to the nearest gas station would be off by miles without adjustment. Curious, isn't it? Even time refuses to move in a straight, uniform line, but more on that in section 18. For now, let's come back to gravity's most subtle mischief, its relationship with motion. You might be sitting still right now, cozy, warm, a little sleepy, but technically you're flying through space at about 30 kilometers per second as Earth orbits the Sun. The Sun itself is orbiting the galactic center at over 220 kilometers per second. And the galaxy, it's moving too. There's no still point, no universal up or straight ahead. Everything's in motion. Everything's curving, including you. Ever heard of the term free fall? It's when gravity is the only force acting on something. Astronauts in orbit, they're in free fall. They're not weightless because there's no gravity. They're weightless because they're falling around the Earth so fast they keep missing it. They're curving forever. That's what an orbit is, falling in a circle. Let that sink in. There's no such thing as staying still in space. If you try, something pulls. If you move, you're curving. Straight line motion. It's just a fairy tale we teach in physics class before we break hearts with relativity. Even black holes, those terrifying voids of gravity, are less like holes and more like dents in the universe's mattress. Drop something in and it doesn't fall in a line, it spirals like water going down a drain. Near the event horizon, space itself bends so hard that the path of light becomes circular. A photon can literally orbit a black hole in what's called a photon sphere. That's right. Light, the icon of linear motion, goes in a circle if you trap it just right. And just in case you were thinking that all this bending only happens in the big stuff, the stars, the planets, the galactic dance floors, nope. Gravity plays with the small things too. Atoms, molecules, dust, all of them are affected, however slightly, by gravitational curvature. If you drop a feather and a hammer on the moon, they fall at the same rate. Not because they're the same shape or size, but because there's nothing to resist the gravity pulling them on the same warped track. That's why that old Apollo 15 experiment is still one of the most oddly satisfying things on the internet. Even your own muscles know gravity's influence. If you spend too long in microgravity, your spine stretches, your bones weaken, and your sense of direction goes haywire. Astronauts come home taller and more confused. Their bodies were designed for a curved space, pulled ever downward. Take away that gentle tug and their systems get fussy. So no, gravity doesn't allow straight lines. It literally warps the playing field. And yet here you are, breathing, relaxed, existing comfortably in a space-time soup that curves and flows beneath you. You don't have to fight it. You just float with it. Every movement, every breath, every sleepy blink of your eyes follows a soft curve written into the fabric of the cosmos. It's not a flaw, it's design. So now you're drifting, not quite asleep, not fully tethered to the waking world either, and just in time because we're entering the part of the universe where nothing travels in a true line, not even a sneeze. It might seem like a strange jump, from gravitational lensing and photon orbits to the violent expulsion of air and mucus, but bear with me, because sneezes, like starlight, are curve-bound little travelers, and they prove a point the cosmos has been quietly making since the beginning. Motion doesn't obey your craving for straightness. It dances. It meanders. It spirals through the chaos like a drunk figure skater in zero gravity. Let's start with the most basic idea: motion in a vacuum. In classical physics, pre-Einstein, pre-chaos, pre-everything falling apart, if you threw an object in space, it would travel forever in a straight line unless something acted on it. Isaac Newton loved that sort of thing. Clean, predictable, very testable. But the second you add anything real, gravity, friction, a molecule of gas, an overconfident elbow, straightness collapses. A sneeze, for instance, travels in a highly chaotic fluid pattern. What might feel like a blast of air jetting forward in a neat line is actually a tangle of mini tornadoes, turbulent eddies, and expanding aerosol clouds. High-speed cameras have revealed that sneezes don't shoot forward like bullets. They bloom, curling outward like the arms of a galactic sparrow. Gross, but also weirdly beautiful. Historians don't often argue about the physics of sneezing, but they do bicker about whether early physicians understood airborne contagion or thought disease rode in straight lines, like an arrow from the sick to the healthy. Miasma theory, the belief that illness traveled through bad air, leaned more into the idea of clouds and vapors, which, for all its faults, at least captured the curve. Now zoom back out. Toss a rock into a lake. You expect it to arc, splash, and sink. But if you filmed that at 1,000 frames per second, you'd see the water droplets curling outward in twisting patterns. You'd watch the shockwave ripple out not as a neat circle, but a warping wavefront deformed by tiny variations in water density, wind, temperature, and the shape of the rock. Nothing about it is straight. Nothing ever really was. Even something as sharp and decisive as a laser beam, light concentrated, collimated, and aimed like the universe's own pointer finger, doesn't travel in a perfect line. It spreads, slightly. It diffracts, bends around tiny imperfections in air. Pass it through a glass of water and it breaks into curves, splits into rainbowed arcs, shatters its linear identity. A laser is disciplined, but not immune. You're starting to get the sense, maybe, that everything curves under the slightest pressure. And that's true, because the universe, it turns out, is built on fields, not lines. Magnetic fields, electric fields, gravitational fields, all of them warp space in ways that defy your middle school diagrams. Motion doesn't happen along neat paths. It rides these invisible slopes, slinking and looping through force gradients that don't care about your need for direction. Picture a charged particle, say, an electron, moving through a magnetic field. Instead of shooting forward, it spirals. Literally. It corkscrews through space in a helix constantly pulled sideways by Lorentz forces. That's not just a theoretical curiosity, it's how auroras happen. Solar particles spiral along Earth's magnetic field lines, crashing into the atmosphere at the poles, lighting the sky in green ribbons of bent energy. And the more chaotic the environment, the more motion surrenders to irregularity. In fluid dynamics, a field where straightness goes to die, there's turbulence, a phenomenon so chaotic it still gives physicists ulcers. A drop of ink in a glass of water doesn't diffuse in a clean line. It whirls, it mixes. It forms swirls and eddies that look like alien landscapes. And in air, that turbulence governs the path of every sneeze, every cough, every dragonfly in flight. It even governs fire. A candle flame dances, flickers, moves with invisible curves written by air currents. A wildfire, terrifying in scale, doesn't rush forward like a bulldozer. It rolls, flanks, backburns, and jumps. Its front line is never straight. It has no front line at all, just probability zones where combustion is more likely to win. And then, of course, there's chaos theory, the science of systems so sensitive to initial conditions that even if they start on a line, they diverge wildly. The famous butterfly effect isn't really about butterflies. It's about how even slight variations, less than a fraction of a degree, can redirect the entire course of a hurricane or a life. Which brings us back to that rock you imagined earlier. Or maybe it was a tennis ball, or your phone flying out of your hand in bed. Doesn't matter. Whatever you throw, wherever you throw it, you're dealing with drag, wind, and gravity, forces that bend its path unpredictably. Try bouncing a ball. You expect it to follow a parabolic arc, a tidy, math-approved curve. But throw it with spin or onto an uneven surface or near a breeze and its motion gets chaotic. Not random exactly, but far from straight. Because friction and spin feed into something called the messiness effect, which causes rotating objects to curve in motion. That's why soccer players can bend a ball around a wall of defenders. They're not defying physics, they're leaning into it. And this obsession with motion, it's everywhere. In architecture and design and simulation. Animators spend lifetimes studying how motion bends, how a character's hair flutters, how fabric moves in wind, how smoke curls into a room. And none of it is straight. Try animating a straight line walk and your character looks stiff, robotic, haunted. Life exists in curves. It's encoded into motion itself. Even your dreams move this way. In sleep, your mind doesn't journey from A to B, it leaps, loops, curls back on itself. A high school hallway becomes your grandmother's kitchen, becomes the surface of Mars. There's no straight path through a dreamscape. Just a spiraling narrative logic that makes sense only in the moment and unravels in daylight. So here you are now, curled beneath a gravity-slicked sky, letting your thoughts wander. Motion, you realize, was never supposed to be linear. Not for stars, not for spit, not for you. The world moves in curves and wiggles and shimmering waves. Straightness is a myth we tell ourselves so we can plan things. But the actual story, the one written into every molecule of motion, is gloriously off track. And isn't that kind of wonderful? You're drifting now, somewhere humid and green and quietly alive. There's a river ahead, wide and glassy, snaking through the landscape like a silver thread left loose by an impatient seamstress. You want to trace its shape with your finger, maybe in the air, maybe on your blanket, but you already know what you'll find. This river, like all rivers, refuses to move in a straight line. Of course it does. Rivers are the universe's most stubborn, beautiful proof that straight lines don't belong in nature. You could try to argue with them. You could bring all your maps, your engineering degrees, your little protractors. Doesn't matter. A river's gonna bend, because that's what flowing water does. It follows the path of least resistance, and that path is almost never, ever straight. Now sure, if you start at the top of a mountain, the water will try to drop in a steep line at first. Gravity is in charge up there and it doesn't play games. But give that water just a few meters to breathe. Let it reach a slope, hit a patch of loose soil, brush up against a stubborn rock, and suddenly the line breaks. The flow starts to curve, first subtly, then wildly. And you end up with meanders. Those gorgeous, looping bends that make rivers look like they're drunk doodling their way across the landscape. And here's the kicker. Those meanders don't form randomly. They grow, like living things. A tiny curve in the river causes water to flow slightly faster on the outside edge, which erodes the bank there. Meanwhile, sediment builds up on the inner edge where the water flows more slowly. Over time, the curve gets more exaggerated, then more, until the river loops like a lazy ribbon tossed across a table. There's even a law, a rule of thumb, that says the average length of a river between bends is about 11 times the width of the river itself. Not because someone planned it that way, because nature, without fail, finds that ratio over and over again. Historians still argue whether early irrigation systems, like those in ancient Mesopotamia, tried to force rivers into straight lines or simply worked with the bends. There's evidence both ways, but most agree. When humans tried to fix rivers, the rivers got even more rebellious. Let's take the Mississippi River as an example. Old Man River has been carving his way through North America for tens of thousands of years, and he does not like being told what to do. Before the U.S. Army Corps of Engineers got involved, the Mississippi changed course frequently, abandoning old paths and carving new ones like a wandering artist. Entire towns would find themselves high and dry, or suddenly underwater, because the river decided on a cosmic whim to swing left instead of right. So we built levees, dams, straight channels. We tamed it. Except not really. The Mississippi still tries to jump course every few decades. There's a hidden threat called the Atchafalaya River, a side channel that's been stealing water from the Mississippi, trying to lure it into a new path toward the Gulf. The only thing stopping it is a complex set of control structures and political panic. Without those barriers, the Mississippi would absolutely take the detour. It's faster, steeper, more efficient. But efficient isn't always convenient for humans, so we've built concrete to fight curves. Still, the curves push back, and not just in big rivers. Tiny creeks, glacial streams, even your neighborhood storm drain, all of them bend eventually. Water hates to travel in a line. Why? Because straight channels increase velocity, which increases erosion, which destroys the very line you tried to build. The river, in its quiet, watery way, teaches the same lesson over and over. The more you force a line, the faster it breaks. Even in engineered canals, meandering creeps in. The Panama Canal has gentle curves. The Erie Canal wound its way through New York with constant adjustments. Every twist was a nod to topography, geology, and human stubbornness. Because even when we crave straightness, we're forced to make peace with the bend. And it's not just geography. The mathematics behind rivers, hydrodynamics, is messy, fractal, and deeply nonlinear. Fluid flow operates in chaotic regimes. You've probably heard of the Reynolds number, right? Okay, maybe you haven't, but let's pretend you have because it sounds impressive. It's a dimensionless number that predicts whether a fluid's flow will be smooth, laminar, or chaotic turbulent. Once rivers hit a certain size and speed, turbulence takes over. And with turbulence comes spirals, vortices, and bends. Every molecule of water, instead of moving forward like a soldier in formation, moves like a dancer in a crowd, twisting, adjusting, colliding with invisible eddies. And the sum of that chaos becomes a river. Flowing, yes, but never straight. Want a fringe fact? There's a river in Peru called the Cañete that has such dramatic meanders it forms oxbow lakes, cut-off bends that create U-shaped pockets of still water. In aerial images, it looks like someone tangled a hose and gave up halfway through. And that's not unusual. Rivers want to form oxbows. It's their version of shedding old skin. They cut off their own loops when the bend gets too extreme. Then they keep going. There's a certain peace in knowing that nature allows for course corrections like that. That even a river, relentless in its forward motion, is allowed to loop, double back, and change its mind. Even more strange, on some planets, scientists have spotted signs of ancient riverbeds. Mars, for instance, shows evidence of long-gone streams that meandered across its surface. Meanders, on another planet, proof that this curving behavior isn't just local, it's universal. Wherever fluid flows across a surface, the straight line crumbles. And so, as you lie there listening to the imaginary sound of a river passing through your mind, maybe you feel it too, that gentle, unhurried motion that doesn't rush toward a point but wanders, loops, lets the banks guide it. Maybe that's how you move through life if you're lucky. Because forward isn't always straight. Sometimes forward looks like sideways. Sometimes it looks like pausing. Sometimes, like a sleepy river curling through an endless valley, it just means not fighting the current. Now you're higher up, elevation-wise, and maybe a little dream-wise too. The trees have thinned, the air has sharpened, and suddenly you're standing in front of something ancient and unapologetically dramatic, a mountain, or maybe it's a whole range. Craggy, towering, jagged as a broken crown. And you, brave little carbon-based life form, are trying to see the geometry in it. But spoiler alert, you won't. Mountains do not care for straightness. They don't rise with clean edges or stack themselves like blocks. Mountains crumple, fold, twist. They grow the way old paper wrinkles in your pocket, suddenly and unpredictably. And their shapes, they defy the very concept of a straight line. Let's rewind a bit. Mountains form when tectonic plates collide or stretch apart, massive, slow-motion catastrophes that unfold over millions of years. The Himalayas, still rising, the Rockies, still adjusting. Earth's crust, you see, is more like a cracked eggshell floating on molten soup than a solid floor. And when those cracked pieces push into each other, rock doesn't politely stack, it warps. It behaves like taffy with a grudge. Folding, faulting, uplift, erosion. These are the tools in nature's mountain-making toolbox, and none of them know how to draw a straight line. If you walk the ridgeline of a mountain range, metaphorically, for now, you'll notice that the higher you go, the rougher things become. Trails switch back endlessly. Cliffs jag upward like crooked teeth. There's no such thing as a straight hike up a mountain, no matter what the trail map says. Your legs zig, your spine zags, and the horizon line tilts just enough to make you question whether you're climbing or just slowly losing balance in a scenic hallucination. Mathematicians have tried to describe these shapes with more and more creative tools over the years. One of the most powerful, fractals. You've probably seen a fractal before. Those endlessly repeating patterns that look the same no matter how far you zoom in or out. Snowflakes, cauliflower, fern leaves, and yes, mountains. The key to a fractal is that it's self-similar at every scale. So whether you're looking at a 100-mile ridgeline or a 5-foot outcropping, the overall texture remains rough, irregular, and uncooperative. There's a famous example in mathematics called the Koch snowflake, a shape created by repeatedly adding smaller triangles to the sides of a triangle. Each time you add more detail, the outline gets more jagged and the length of the perimeter increases forever. It never smooths out, never simplifies. And that's how mountains feel, chaotic at first and then more chaotic the closer you look. Historians still argue whether ancient cultures interpreted mountains as homes of gods because of their physical dominance, or because their incomprehensible shapes broke the human sense of spatial order. Either way, there's something mystical about a thing so big and old and bent. Let's dig down literally. The layers inside a mountain tell the story. Sedimentary strata, originally laid down in flat horizontal sheets, have been warped into impossible angles by tectonic stress. You'll see rock layers standing on end, twisted like saltwater taffy, crumpled into sharp V's. And remember, these layers started flat, but Earth had other ideas. Geologists use terms like anticline and syncline to describe these bends, folds that push rock into arcs and dips. But those terms don't fully capture the artistry, the randomness, the occasional nonsense of it all. And erosion, oh, it loves to get involved. Water, wind, and ice chisel away at the peaks, but not evenly. Softer rock wears down faster. Cracks widen irregularly. The result is a shape that evolves constantly. You never visit the same mountain twice. Even rock slides and avalanches fall in curves. They start with a crack, then a lurch, then a tumbling mess of movement that arcs and flutters like fabric unraveling in slow motion. Nothing falls straight, not really. Not when gravity, terrain, and friction get their hands on it. Now there's a concept called topographic ruggedness. It's a way of measuring how uneven a landscape is, how violently it deviates from flatness. Mountain ranges top the charts, but even then the numbers don't quite capture the visual complexity. You have to see it, feel it. Let your eyes follow a ridgeline only to be tricked by a false summit, then another, then one more. Some mountain ranges, like the Dolomites in Italy, are so jagged and bizarre that they look like abstract sculptures. Others, like the Appalachian Mountains, are worn down, rounded, gentler in their wrinkles. But even those soft-edged elders still resist straightness. They're just hiding their chaos under a blanket of moss and time. Let's throw in a fringe detail here. On Mars, there's a mountain called Olympus Mons. It's the largest volcano in the solar system, towering over 70,000 feet tall, but weirdly, its slopes are relatively smooth. Why? Because Mars doesn't have active plate tectonics. Its crust doesn't shift and crumple the same way ours does. Olympus Mons grew up vertically, undisturbed like a giant pimple on a sleepy face. No fault lines, no folding. Just one long belch of lava, over and over again. So even in the universe, you get the occasional exception. But Earth's mountains, they fight, they fold, they never conform. And what about climbing them? Ever noticed how even the most direct route up a mountain involves constant zigzagging? Switchbacks are designed to make ascent manageable, but they also follow the landscape's contour. You don't fight the slope, you negotiate with it. Every step you take is a sideways motion in service of upward motion. It's not just practical, it's poetic. Even in the metaphorical mountains of life, yep, we're going there, progress doesn't happen in straight lines. You climb, you backtrack, you find a ridge, follow it sideways for a while, then climb again. Nature built that model into the ground itself. So as you lie there, maybe picturing some distant peak in the moonlight or remembering a hike that left your knees aching and your soul somehow quieter, remember this. The mountain wasn't being difficult, it was being honest. It was showing you that real structure doesn't need symmetry. That truth comes jagged. That sometimes the most stable thing is something crooked that never breaks. Lightning doesn't travel in a straight line. You've probably guessed that by now. But when you really stop to picture it, when you slow it down in your mind's eye to less than a frame per second, it becomes even more obvious. You're watching an angry zigzag stutter its way through the sky. A split-second snarl of energy, branching, jittering, flashing down in fits. If the universe were fond of straight lines, lightning would be the poster child. It's electricity, after all, raw voltage taking the fastest possible path from cloud to ground, right? Wrong, absolutely, deliciously wrong. Lightning is a crooked dancer. And now here in the safe, dim glow of your imagination, you're standing out in an open field. It's humid. The air is thick and waiting. You feel that tingle in your arm hairs, the metallic pressure in your sinuses. A storm is coming. The clouds above look like charcoal stirred into milk, boiling, layered, bruised. Then, a flash. You don't hear it yet, that comes later. First, you see the shape. It doesn't look like a clean jab from the sky. It looks like a shattered vein, a sideways growing crack that suddenly changes direction, then forks again, and again. Because lightning isn't one flash, it's many. What we see as a single bolt is actually a flickering stream of connections, all working together in chaotic relay. The primary path of lightning, the one you see, is known as the main discharge or return stroke. But before that return stroke can happen, the air must be prepped, ionized, lured. Enter the stepped leader, that's right. Lightning begins with a hesitant, invisible dance. A thin, negative charge drops from the cloud in small jumps, each about 50 meters long, stopping, probing, branching, pausing. It's not a confident move. It's a wandering one, seeking the path of least resistance. Meanwhile, positive charges from the ground surge upward to meet it. Little invisible feelers, streamers, climb trees, buildings, and yes, even you, if you happen to be standing around doing something deeply questionable like flying a kite. When a leader and a streamer finally connect, they form a channel. And in that moment, the real show begins. The return stroke blasts upward through the newly formed path, lighting up the sky with the brilliant crack we call lightning. But even then, it doesn't move straight. The channel is already jagged. It's zigzagged into existence. And electricity, ever the opportunist, simply follows the weird, twisty corridor it helped make. Historians still argue about who first realized lightning wasn't just a straight jolt. Ben Franklin's kite story is famous, but the nuances of the discharge weren't understood until high-speed photography came into play in the 20th century. Before that, lightning was simply painted as a divine spear. Straight, clean, judgy. But science caught up, and it found something much more chaotic, much more honest. There's even a special name for that crooked bolt you sometimes see dart sideways across the sky, never touching the ground: anvil crawlers. These horizontal lightning bolts slither through the upper parts of a storm cloud, branching like ivy across the heavens. They're beautiful and a little spooky, less Zeus, more Lovecraft. And sometimes lightning doesn't just flash downward or sideways, it goes up. That's right. Lightning can rise from the top of a tall building or antenna tower and stretch upward into the cloud. These are called upward lightning events, and they're weirdly graceful, smooth arcs rising against gravity like the ghost of a sparkler held backward. Now add in ball lightning, a rare, still mysterious phenomenon where glowing orbs of plasma reportedly float along surfaces, sometimes entering buildings or bouncing gently across lawns. Historians and physicists alike argue over whether it's real, misunderstood, or a hallucination brought on by static, fear, and folklore. But if it is real, it's the most unstraight electrical phenomenon we've got. A curve, a sphere, a glowing, wandering child of the storm. But here, where it gets more scientific, lightning's crookedness follows the rules of fractals. Remember those from the mountains, nature's endless patterns repeating at every scale. Yeah, lightning is a fractal. Its branching follows rules described by fractal mathematics. The same patterns appear in small discharges in a lab as in gigantic strikes across a sky. The jaggedness isn't random, it's complex. The chaos has structure. You could model it with algorithms, and in fact, animators do just that to create believable lightning in films. Want a fun fact? The average bolt of lightning is 5 times hotter than the surface of the sun, around 30,000 Kelvin. That much heat shoved into a twisting, unstable corridor of ionized air. It's not just bending the path, it's tearing it open. And that thunder you hear afterward, that's the air collapsing in on itself after being instantly heated and expanded by that lightning. A shockwave, a crack, another reminder that nothing, not even the aftermath of a strike, spreads in a line. The sound travels outward in waves, ricocheting off hills, buildings, clouds, reaching your ears as a staggered boom. Sometimes a single bolt produces multiple claps of thunder, each distorted by the environment it hits. Even the lightning rods we build, the tiny little spikes perched atop buildings, don't attract lightning in a straight shot. They influence it, guide the path, encourage the strike to follow a slightly safer route. But the moment of contact, still jagged, still primal. So, as you lie here in your pillow-bound observatory, remember this. The next time you see a storm roll in, and lightning forks down like cracked glass across the sky, you're not just watching electricity. You're witnessing a cosmic tantrum following rules no human hand could draw. It's one of nature's clearest messages. The path of energy, even raw power, is rarely straight. It branches, doubles back, flickers with indecision, and then only then it connects. Just like you do sometimes. You're inside your own body now. Not in a weird sci-fi shrink-ray way, no fantastic voyage submarines or ominous heartbeats, but gently, quietly, as if your thoughts have turned inward and started tiptoeing through the hallways of your biology. And let me tell you, those hallways, they twist. Because evolution, bless its improvisational heart, absolutely hates a straight line. Oh, it tries sometimes. You've got bones, after all, ribs and femurs and phalanges that look fairly linear. But once you dig beneath the surface, into the nerves, the vessels, the inner design, you find loops, redundancy, detours, systems that wind and double back on themselves like someone was designing a circuit board with oven mitts on. Let's start with the recurrent laryngeal nerve, a lovely little anatomical joke that evolution has been playing on mammals for millions of years. This nerve connects your brain to your voice box. Seems simple enough. Should be a straight connection, right? Oh no, not even close. Instead of taking a direct route, the recurrent laryngeal nerve dives all the way down into your chest, loops around your aortic arch. Yes, that massive artery near your heart, and then comes back up to reach your larynx. It's like taking a 12-hour layover to get to a cafe down the street. Why? Because when necks were shorter, back in our fishy evolutionary ancestors, this path made sense. As necks lengthened, the nerve got stretched and dragged along for the ride. Evolution doesn't rebuild from scratch. It just modifies, which means you now have a nerve in your throat that takes a scenic route through your chest for no good reason. Historians still argue whether this kind of inefficient design is evidence of blind, stepwise evolution, or if there were hidden adaptive advantages. But either way, that nerve is a winding little monument to nature's refusal to take a shortcut. And that's just the start. Let's take a tour of your intestines, or just picture them. Your small intestine alone stretches about 20 feet, coiled inside your abdomen like a soft, angry snake who just found out its rent went up. That's not a gentle loop. That's a biological pretzel. Why so twisty? Surface area. More twists equals more space for absorption. Your digestive system is a master of turning curves into function. Even the villi inside your intestines, those microscopic finger-like projections, add layers upon layers of inner curves. If you could flatten all that surface area out, it'd cover something close to a tennis court. And your circulatory system, also a mess. Blood vessels branch, divide, reconnect. Arteries loop around bones, duck under muscles, double back. You think your heart could just pump blood in a straight line to your toes and call it a day, but nope. It takes a tangled tour through countless detours. The veins in your legs alone have backup systems, called venous anastomoses, to reroute blood flow if a path gets blocked. That redundancy, those curved bypasses, are part of the reason you don't pass out every time you stand up too fast, or at least not always. Even your fingerprint, the soft swirl pressed onto your screen 1,000 times a day, is a tribute to curved redundancy. Those ridges aren't just aesthetic. They increase grip, sensitivity, and surface feedback. And they loop, whorl, and arc in patterns so unique that not even identical twins share the same design. Now let's zoom into your DNA, your very code. That spiral ladder you've seen in textbooks, the double helix, is not only not straight, it's coiled on a coil. DNA wraps around proteins called histones, forming loops, which then fold into loops of loops, ultimately packaging 6 feet of molecular instructions into a microscopic nucleus. If DNA were straight, it wouldn't fit. Your very essence is written in a spiral. And in your brain, oh, the folds. Your cerebral cortex is all gray matter spaghetti, folded and crumpled like a brain-shaped crepe. Why? Because folding allows for more neurons in less space. A smooth brain is a rare and typically tragic condition. Your thoughts require the wrinkled landscape. Intelligence doesn't emerge from straight lines. It rises out of grooves. Fringe fact for your late-night file: gastropods, snails, and slugs have their own version of a loop-the-loop nerve problem. It's called torsion, and during development, their entire body twists 180 degrees, flipping the location of organs. This puts their anus directly above their head, which is not ideal, but evolution shrugged and kept going. Now consider your lymphatic system, the unsung hero of your immune response. It's a lazy river of fluid, twisting through tissues, looping through lymph nodes, filtering waste in a network that defies linearity. It doesn't even have its own pump. It moves via muscle motion, breathing, and sheer willpower. And yes, your respiratory system gets in on the loopiness too. Your bronchi split again and again, forming a branching fractal structure all the way down to alveoli, tiny air sacs where gas exchange happens. Straight pipes wouldn't work. You need surface area. You need curves. Even embryonic development begins with a spiral. The cells of an early embryo divide and twist in a process called spiral cleavage in some species. It's nature's first doodle before bones or organs form. A soft little twist that says, hey, let's not do this in a line. And that evolutionary bias, it shows up in every living thing. Trees don't grow in straight lines. Their branches twist toward sunlight. Vines spiral around poles. Animal horns curl. Fiddler crabs regrow lopsided claws. Nature doesn't favor symmetry or straightness. It tolerates it, occasionally, when convenient. Even your hair, yes, that stubborn curl or wave you tried to tame in middle school, is evidence of asymmetry at the follicle level. A perfectly circular follicle produces straight hair. Oval ones, curls, kinks, spirals, All your head is doing is following the path of genetic least resistance. And speaking of genetic drift, even evolutionary paths don't follow straight trajectories. Species branch, split, loop back via convergent evolution. A whale and a bat both evolved echolocation. Cacti and euphorbias, plants from opposite ends of the world, evolved spiky forms independently. Evolution doesn't march forward. It meanders, stumbles, fakes its own death, and occasionally walks into a wall before inventing flight. So here you are, a bundle of soft curves, looped systems, and elegant redundancies wrapped in skin. And all this time, someone probably taught you to walk a straight path. Think straight, stay on the straight and narrow. But your biology tells a different story. You were never built to move in a line. You were built to twist, to adapt, to reroute when needed. You are not a line, you are a labyrinth. And isn't that just the best news you've heard all day? You're indoors now, safe, cozy, and surrounded by right angles. At least that's the illusion. Look around your imagined room. The walls meet the floor at 90 degrees. The ceiling is flat, the windows rectangular. Shelves run parallel, furniture squared off like geometry homework. This, you think, must be where straight lines finally win. Except no. This is where the war on wiggle starts. Human architecture is a defiant experiment in keeping things straight despite a universe that really doesn't want to cooperate. We build rigid rectangles in a wobbly world, and it takes constant effort and endless correction to hold those lines. That's why every building you've ever entered is secretly rebelling. Let's start with the walls. When architects draft a structure, they assume flatness, straight beams, vertical columns, horizontal floors. But the moment construction begins, real-world forces show up and start ruining everything. Gravity pulls, moisture seeps, materials expand and contract. A house built on a sunny day will be subtly different by nightfall as the air cools and the wood breathes. Wood especially is not your friend in this fight. It swells when it's humid. It shrinks when it's dry. It twists and warps in slow motion like it's trying to sneak out of your living room unnoticed. That's why doors stick in summer and suddenly swing freely in winter. They're bending, subtly, relentlessly. Engineers fight this with tricks. Floating floors, expansion joints, load-balancing reinforcements. The taller the building, the more complex the dance. Take the Burj Khalifa, the tallest building in the world. It sways several feet in the wind on purpose. It has to. If it didn't, it would crack under its own refusal to flex. So engineers designed it like a giant reed, graceful, bendable, and deeply curved in its soul, even if it looks straight to the eye. Historians still argue whether ancient builders in places like Egypt or Mesopotamia understood the true forces at play, or if they just built chunky enough structures to absorb any imperfections. The Great Pyramid of Giza, for example, seems straight. Its edges look sharp from afar, but those limestone blocks, irregular, varied, laid in a way that tolerates slight shifting without collapse. Meanwhile, in Gothic cathedrals across Europe, engineers developed flying buttresses, those lovely sideways arches, not just for style but to manage force. The tall walls couldn't stand perfectly straight on their own. The arches spread the weight, allowed flexibility, and made those impossibly tall windows possible. You know, the ones that definitely wouldn't exist if straight lines ruled unchecked. Even modern buildings cheat. Take the Parthenon in Athens. Its columns at a glance seem perfectly vertical, but they're not. They lean inward very slightly and they bulge a bit in the middle, a design trick called entasis. Why? Because perfectly straight columns look bowed to the human eye. So the Greeks compensated with a gentle curve to create the illusion of straightness. Yeah, the only way to make something look straight was to not build it straight. Welcome to architecture's little secret. All these lines you see, they're curated, coaxed, fudged. Even glass, which you might assume to be flat and straight and all grown up, sags over time. That's right, glass is technically a supercooled liquid. It doesn't flow like molasses or anything, but it does shift. Old cathedral windows are thicker at the bottom, not by much, but enough to prove, Even the most transparent straight line eventually goes soft. Now think about bridges. Straight, not even close. Most bridges use curves, arches, parabolas, catenary lines to distribute stress. That iconic arc in the Golden Gate Bridge, it's not decorative, it's math. The cables and towers form gentle curves that spread the weight of traffic, wind, and time. And suspension bridges, they don't hold themselves up, they hang. The main cables dip in perfect curves and the roadbed hangs from them in vertical drops. It's a system that relies on bending, on dynamic tension. Make a suspension bridge too rigid and it fails. Speaking of failure, have you ever heard of the Tacoma Narrows Bridge? Built in 1940, it was long, elegant, and supposedly strong. But it ignored how wind interacts with flexible surfaces. On November 7th, just months after opening, the bridge started to oscillate. The wind hit the structure just right, like blowing across the mouth of a bottle, and the whole thing began twisting. Not side to side, not up and down, torsionally, like a ribbon in a breeze. A few hours later, it collapsed in a dramatic, spiraling failure now studied by every architecture student forever. A perfect example of what happens when you trust straightness more than motion. And you thought your IKEA bookshelf was unstable. Want a fringe detail? The Japanese art of wood joinery creates buildings without nails or screws, just interlocking wooden pieces. These joints are designed to move. In earthquake-prone areas, it's not the stiffest building that survives, it's the most flexible. The one that lets go a little, the one that trusts the curve. Even your own home, wherever it is, rests on foundations that shift. Soil settles, water seeps in, tiny tremors wiggle the earth. That's why doors misalign over the years, why floors creak, why houses settle, as people like to say, which is just a polite way of describing an extremely slow collapse that we all agree to ignore. And cities, they don't grow in lines. Urban planners try, bless them, to grid things out. Manhattan is famous for its rigid street grid, but even there, Broadway slices diagonally like a misbehaving child and no one stops it. Cities evolve with curves based on rivers, hills, politics, accidents. Roads meander. Alleyways twist, infrastructure adapts. Ever driven in Boston? Then you know. So here's the truth you've suspected all along. Straightness in architecture is artificial. It takes more effort, more math, and more compromise than any curve ever has. Curves work with nature, lines fight it. And yet we keep trying, maybe because straight lines feel safe. They suggest order, logic, permanence. They make space feel conquerable. But you now, lying back and listening, know better. You've seen the edges soften. You've learned the buildings are breathing. You felt the floor tilt a little when no one else noticed. Architecture isn't a monument to straightness. It's a truce, a compromise, 1,000 little curves hidden beneath drywall and paint. And if the walls could talk, they'd probably say, "Thanks for not pushing too hard. We're doing our best." Let's go farther now, not just beyond your room or your city or even the gentle arc of your planet's horizon. You're floating, slowly, towards something more abstract, something that turns all those tidy lines and familiar angles into warped suggestions. That something is spacetime. And somewhere along this quiet, drifting journey, you feel it happen. Geometry breaks. All the nice little rules you were taught, parallel lines never meet. The shortest distance between 2 points is a straight line. Angles in a triangle always add up to 180 degrees, start to wobble, subtly at first, then wildly. It's as if reality took a yoga class and got really into bending. You've entered the domain of general relativity, and Euclid is screaming softly in the background. In flat classical geometry, the kind you probably doodled on math worksheets, space behaves itself. It lies still, angles obey, shapes are polite. But Einstein ruined that party in 1915 by suggesting that space itself could curve. And not only space, time too. Space-time is a fabric, not a metaphorical one. A real, measurable, warping thing that responds to mass and energy. Mass tells spacetime how to curve, and spacetime tells objects how to move. Which means nothing moves in a straight line anymore. Picture a planet orbiting a star. You might have imagined it tracing a loop in the vacuum of space, pulled inward by gravity like a ball on a string. But that's not quite right. The planet is actually moving straight as it can, along a path called a geodesic, except that geodesic itself is bent, because the space it travels through is curved by the star's mass. Imagine setting a marble on a trampoline where a heavy bowling ball sits in the center. The marble rolls around it in a loop, not because it's being pulled, but because it's following the curve of the trampoline. That's a geodesic. And that's how planets orbit stars, how moons orbit planets, how light bends around black holes. They're all following bent paths that feel straight to them. That's the betrayal. Even when you think you're going straight, the space beneath you is lying. Historians still argue whether Einstein's curved spacetime was a natural evolution from Newton's ideas or a complete upheaval. Newton's gravity was a force that acted at a distance. Einstein's is geometry itself, reality reshaped by the presence of mass. And in case you think this is just for giant things like stars and galaxies, remember, even standing here on Earth, you are living in curved space-time. Clocks run differently at the top of a mountain versus sea level. GPS satellites account for relativity just to keep your directions accurate. Your phone wouldn't work if we ignored Einstein. Let's talk about light again. Once considered the ultimate straight-line traveler, but even photons, the very particles of light, are caught in the curve. Light passing near a massive object like a galaxy gets bent, not because it slows down or changes direction on purpose, because it's following the straightest possible path through warped space. That bending, it creates phenomena like gravitational lensing, where light from a distant galaxy bends around a closer one and forms arcs or even full rings. We can see these arcs in space photos. Galaxies smeared like oil on water. Cosmic lipstick prints, all because the geometry beneath them broke. And then there's the precession of Mercury. For years, Newton's equations couldn't quite predict Mercury's orbit. It wobbled slightly. A tiny curve in a curve. Einstein's relativity nailed it, because it understood that near the sun, space-time is warped enough to tweak Mercury's path just slightly with every loop. Oh, and those black holes. They're not holes. They're wells, bottomless pits in the fabric of space-time. Get too close, and the curve becomes so extreme that even light can't escape. At the event horizon, the edge of the black hole, the geometry becomes so broken that all known physics just sort of shrugs and looks away. And then there's time. We tend to think of time as straight. Past leads to present leads to future. Tick-tock forward. But space-time doesn't make that promise. Near massive objects or in extreme conditions, time bends. Literally. A second for you might be a different second for someone orbiting a neutron star. Astronauts aboard the International Space Station experience time slightly slower than we do on Earth, due to both velocity, special relativity, and altitude, general relativity. It's not enough to notice, but it's measurable. If they spend enough time up there, they actually come home younger by a few milliseconds. Congratulations! Time travel is real and incredibly boring. But here, where it gets wild. In curved geometry, parallel lines can meet, or diverge forever. Triangles can have angles that add up to more than 180 degrees, or less. There's even something called non-Euclidean geometry, the math of curved spaces, where straight becomes subjective. Draw a triangle on a balloon. See how the lines curve outward. Add up the angles. They'll exceed 180 degrees. Now draw one on a saddle-shaped surface. Those angles will fall short. Your triangle's properties depend entirely on the surface it lives on. And guess what? That's us. We live on and in a curved surface, a curved universe. We've even mapped it partially through cosmic microwave background measurements. The early light of the universe, stretched across billions of years, reveals subtle curvature. Current data suggests our universe is very close to flat, but not perfectly. That flatness might just be a local condition, like a road that seems straight until you zoom out and realize it curves with the Earth. So when you think of a straight path through the cosmos, there's no such thing. Every beam of light, every planet's orbit, every second that passes is bent just slightly by the mass nearby. Every line is a lie told by curved space. And maybe that's comforting. Maybe it means you're allowed to change direction, to loop, to spiral into something new. Maybe the idea of a straight life or a direct path was always a myth. Even the universe doesn't live that way. It bends, constantly, beautifully. So you curl up a little deeper, your thoughts caught in the curve, and you realize that geometry never broke. It just evolved. You're not falling exactly, but you're descending, gently, warmly, downward through layers of green. You're surrounded now by stems and leaves and petals so close they seem to breathe with you. This is a quieter realm where the grand curves of galaxies give way to something more familiar, the slow, patient spirals of plants. And wow, do plants love a spiral. Look at a sunflower. Go ahead, picture one right now. That cheerful yellow face. But don't stop at the petals. Zoom in like you're tracing the pattern with your mind. You'll notice it spirals, inward, outward, clockwise, counterclockwise, and not randomly, not sloppily. Those seeds arrange themselves in an elegant mathematical pattern known as the Fibonacci sequence. You've heard of that one probably. It's a series of numbers where each is the sum of the two before it. 1, 2, 3, 5, 8, 13, and so on. In plants, this sequence shows up as the number of spirals in the arrangement of leaves, seeds, or petals. A sunflower might have 34 spirals in one direction and 55 in the other, or 89 and 144. Always Fibonacci numbers. It's not a whim, it's efficiency. Packing seeds in a spiral ensures that none overlap and everyone gets its fair share of sunlight, water, and space. The golden angle, approximately 137.5 degrees, is the magic number that separates each new seed or leaf from the previous one, creating a pattern that avoids stacking or crowding. Straight lines can't do that. Only spirals can. Historians still argue whether the Fibonacci sequence was discovered in plants first or if mathematicians like Leonardo of Pisa, that's Fibonacci's real name, retroactively saw it in nature. But it doesn't matter. The spiral came first. Nature wrote the math. Humans just finally noticed. And the spiral doesn't stop with seeds. Climb a pinecone in your imagination, or better yet, a pineapple. These fruits are spiraled too. Rows of diamonds running diagonally in both directions. Count them, you'll find Fibonacci numbers again. It's everywhere. That spiral is called a phylactic pattern, and it governs how leaves grow on a stem. If they grew straight across from each other, they'd block one another from the sun. But twist them, offset them by that golden angle, and suddenly each leaf has its own spotlight. You lying there, breathing softly, are already full of spirals. Your cochlea, the part of your inner ear that processes sound, is a perfect spiral. The hair inside it detects different frequencies depending on where they hit. Low tones near the center, high tones near the edge. It's a spiral equalizer built into your skull. And look again at your fingerprint, that loop or whorl on the pad of your thumb, spiral. Your hair, if left to its own devices, might spiral too. The way a vine wraps around a pole, the way morning glory climbs. That's called circumnutation, and it's how climbing plants find their way upward. They twist and reach, adjusting for light and gravity. It's movement, yes, but in a slow, winding dance. Even DNA, the code of life, is a spiral, a double helix to be precise. Two strands twisted around each other like twin corkscrews. This shape isn't just pretty, it's functional. The spiral allows for compact storage and stable replication. If DNA were a straight ladder, it wouldn't fit inside your cells. It would tangle, break. But spiraled, it packs 6 feet of genetic material into a microscopic nucleus. So spirals are efficient, spirals are strong. Spirals are everywhere, and sometimes they're cosmic. Galaxies like your own cozy Milky Way are vast spirals. Stars arranged in sweeping arms, curved by gravity and motion over billions of years. Scientists believe these spirals aren't fixed structures but density waves, patterns that move through stars like a traffic jam through cars. The stars orbit, the pattern persists. Spirals, again, as the most stable shape for something spinning through curved space. And while we're getting poetic, hurricanes spiral too. So do whirlpools. So does a draining bathtub. Whenever motion meets rotation, spirals emerge. Water, air, fire, even galaxies spin and curl and form these patterns over and over. Want a fringe fact? The Nautilus shell, often mistaken as a perfect golden spiral, actually follows a logarithmic spiral, but not quite the ideal Fibonacci curve. Still, its pattern is breathtaking, and it's been used in everything from art to architecture as a symbol of divine proportion, eternal growth, or just good design. Speaking of design, humans can't resist the spiral either. Architects build spiral staircases for space efficiency and aesthetic appeal. Sculptors love the tension of a form that twists. Even dancers, think of a pirouette, use spiraling motion to conserve energy and balance. And what about your habits, your thoughts? They spiral too. Not always in a bad way, sometimes in a sleepy, comforting way like now. One thought curling into another, a memory looping back to a feeling spiraling into a dream, not linear, not even logical maybe, but real, familiar. That's the nature of the spiral. It doesn't return to where it started, not exactly. It passes close, again and again, expanding or contracting with each turn. Like how you revisit old memories with new understanding. Like how a sunflower spins its seeds outward from a center you can't quite see. And that's the thing, straight lines are rare in nature. They require tension, force, enforcement, but spirals, they emerge, they persist. They spread gently, efficiently, infinitely. So now in this moment, your breath is a spiral too. Inhale, exhale, not just in and out, but around. Your chest rises and falls like waves circling a shore. You're still now, but the motion continues. The spiral is how nature grows, moves, listens, dreams. It's not just a shape, it's a philosophy. And it welcomes you. Now tilt your head back just a little. Imagine the ceiling above you falling away, revealing not just the sky, but the deep, dark everything beyond it. The stars don't twinkle here, they blaze. The moon doesn't glow white, it gleams with the pale silver of old bone. And the blackness, it's not empty, it's moving. Because space isn't still, it's not quiet, and it's definitely not straight. This is the part of the story where even the idea of a line starts to feel quaint. Because in space, there's no such thing as sitting still, and even if you could, the space around you wouldn't let you stay that way. Space expands. Not like a balloon slowly puffing up, not like a ripple in a pond. It's weirder than that. Every patch of space between galaxies is stretching, not into something, not from something. It's not that kind of expansion. The space itself is growing, pulling galaxies apart like breadcrumbs floating on rising dough. It's called the metric expansion of space, and it means that over time, the fabric of the universe gets bigger, which means a straight line across it doesn't stay straight for long. Draw a line on a balloon. Now inflate the balloon. Your line stretches, curves, warps. Its endpoints are farther apart, and the surface beneath it has changed shape. That's what's happening to the universe right now, as you lie there with your blankets tucked around you. And you can blame it on a mysterious little something called dark energy, an invisible force that makes up roughly 68% of the universe and is pushing space apart faster and faster. We don't know what it is. We just know it exists because galaxies are receding from each other at accelerating speeds. Even light can't keep up in some places. Some galaxies are moving away from us so fast, their light will never reach us. Goodbye, straight line communication. Historians, well, Cosmologists still argue whether this expansion is uniform or if local bubbles of spacetime might stretch differently. But the consensus is clear. Whatever is happening, it's not linear. Even on smaller scales, space isn't passive. It ripples. Every time two black holes collide, they send out gravitational waves, tiny compressions and stretches in the fabric of spacetime itself. In 2015, we finally detected one of these waves using an exquisitely sensitive machine called LIGO. What did it see? Two black holes spiraling into each other and merging, 1.3 billion light-years away, sending out a ripple that warps space right here on Earth by a fraction of an atom. Not much, but real, measurable. Space is bouncy. So your imagined straight line across the universe. It would jiggle, sway, undulate like a plucked string as waves pass through it. Even the cosmic background radiation, the afterglow of the Big Bang, has slight irregularities. Those tiny temperature fluctuations mark the earliest density differences in the universe. They're the reason stars and galaxies formed, and they're not arranged in lines. They're clumpy, lumpy, chaotic in just the right way. Now imagine trying to draw a line through that chaos. You'd have to adjust constantly for motion, for warping, for gravitational lensing, expansion, redshift, curvature. Your line would look more like a cosmic roller coaster by the time it reached anything meaningful. And then there's rotation. Galaxies spin, not just the spiral ones, all of them, and their stars don't move in clean circles. Their paths wobble. They move through gravitational arms like dancers stepping through waves of density. The shape of a spiral galaxy isn't static. It's a ripple, a pattern, a dance written in billions of points of light. Our own solar system, also spinning. The Earth orbits the Sun, yes, but the whole solar system is also orbiting the center of the Milky Way. And the Milky Way, it's part of a larger cluster, which itself is falling toward another cluster in a gravitational ballet. If you could trace the path of the Earth through space, not just its orbit, but its movement through the galaxy, through the universe, it would look like a corkscrew, a spiral, a looping helix launched forward at breathtaking speed. Even your own body is carried along that path. You're not still, not even close. You are, at this very moment, traveling at around 1.3 million miles per hour through space, and yet your blanket hasn't moved an inch. Isn't that nice? But what about direction? Isn't that at least straight? Not really. Space doesn't have a center, or an edge, or an up. You could pick any galaxy and call it the center of expansion, and you'd be right, because everything's moving away from everything else. Not in a ring, not in a line, in all directions. Even straightness, when you get down to it, is local. On a small enough scale, things appear linear. Roads, rulers, your countertop. But zoom out just a little and you realize those lines only make sense in tiny pockets where space behaves nicely. Beyond that, it's all bend and stretch and warp. Want a fringe example? Cosmic strings, hypothetical defects in spacetime left over from the early universe, would be the closest thing to a straight line in the cosmos. If they exist, they'd be unimaginably thin and unimaginably long. But even they'd curve slightly under the weight of gravity or the expansion of space. So here's a gentle thought to hold onto as you drift. The universe doesn't move in lines. It pulses, it flows, it undulates. The stars are never still. The galaxies never hold their breath. Space is a restless sea, and even the vacuum itself expands like a sigh that never ends. Your life, it's happening on a planet caught in a spiral, inside a galaxy caught in a swirl, inside a universe expanding faster than light. And yet you're okay. You don't need to move in a line. You never did. You were built to curve, to sway, to follow the bends in the road and still find your way forward. So lie back now. Let the stars spin overhead. Let the invisible waves of space ripple through you like a lullaby played in geometry's softest key. You're part of it, all of it, and nothing is straight. Picture this, a steaming mug of coffee in your hands. You give it a little stir, slow and easy, and for a moment, just a moment, it seems like the swirl you've made is smooth, predictable, a clean spiral curling from the spoon outward, like something designed by a particularly minimalist planet. But wait. You keep watching, the motion spreads, the surface trembles, little eddies appear at the edge, a few lazy bubbles drift off course, and beneath that deceptively calm surface chaos is brewing, literally. Congratulations, you've just created turbulence. And turbulence, dear sleepy traveler, is where straight lines go to die. If the rest of this bedtime tale has taught you anything, it's that the universe seems to have a personal vendetta against clean geometry. But nowhere does that vendetta become so delightfully dramatic as in the wild, swirling world of fluid dynamics. When a fluid, be it air, water, coffee, or plasma, flows calmly, it's called laminar. Layers slide past each other in orderly fashion like pages in a book. Engineers love laminar flow. It's predictable, stable, soothing. But push it just a little, stir it too hard, pour it too fast, increase the speed or the temperature or just look at it funny, and that tidy flow snaps. Enter turbulence. Turbulence is a chaotic, non-linear, unpredictable mess of whirls and eddies. It's fluid flow that's had too much caffeine and no adult supervision. And once it starts, it's incredibly difficult to stop. That spoon in your coffee, you set off a miniature version of a weather system. It would take a computer thousands of equations to model what's happening inside that cup right now. Every swirl has a smaller swirl inside it, and that swirl has another inside it. Fractals again. Even the world's top physicists still struggle to fully describe turbulence. One of the 7 Millennium Prize problems, the most famous unsolved math questions, asks for a complete explanation of turbulent flow in fluids. There's $1 million prize for whoever cracks it. So far, no one. Historians still argue whether Leonardo da Vinci was the first to seriously study turbulence. He sketched water vortices in incredible detail. But it wasn't until the 19th and 20th centuries that scientists started to wrestle with the math. And even now, it remains one of the most challenging problems in physics. Because turbulence, unlike almost anything else in classical physics, refuses to behave. And here's the poetic part. You encounter it every day. When wind rustles leaves, when air moves through your nose, when cream swirls in your coffee, when you flush the toilet or wash your hands or fly through a patch of rough air. It's all turbulence, motion-resisting lines, fluids refusing form. Want a fun fringe detail? Jupiter's Great Red Spot, that giant storm spinning on the gas giant's surface, has been churning for at least 400 years. It's a textbook example of turbulence on a planetary scale. A supervortex born from chaotic flow, caught in a tug-of-war between atmospheric layers and stubbornly refusing to dissipate. Or take ocean currents. On the surface, the sea may look calm, but beneath it, layers of swirling water, currents colliding at different depths and temperatures, eddies forming and dissolving, energy cascading from big swells to tiny ripples. The motion is never linear, never smooth. The ocean doesn't flow like a river, it writhes like a living thing. And speaking of rivers, yes, them again, they're full of turbulence too. That bubbly froth you see around rocks and rapids, that's air getting sucked into fast-moving water as it tumbles over itself in chaotic loops. The same flow that shaped the curves we talked about back in Section 7 is ruled by turbulence. In fact, it needs it. Without that messy motion, sediment wouldn't stir, erosion wouldn't happen, rivers would stagnate. Turbulence creates change. And let's not forget your own body. Blood flows through your arteries in mostly laminar paths until it hits a curve or a narrowing and then it swirls. Surgeons and biomedical engineers model this constantly. Too much turbulence, risk of clotting. Too little, risk of stagnation. You're a walking, breathing fluid dynamics experiment with your heart as the pump and your arteries as the pipes. And oh, the air you breathe. The way it moves through rooms, around corners, over hills. Ever wondered why smoke doesn't rise in a straight column? Why it wiggles and twirls and splits like it's dancing to its own music? Turbulence. Airplanes, they don't fly in still air. The atmosphere is full of invisible motion. Jet streams, updrafts, pockets of warm air. Pilots have to constantly adjust for these shifts, some of which are unpredictable even with modern weather tech. That moment when your plane wobbles and your stomach flips, that's not pilot error. That's the sky refusing to hold still. Even fire dances with turbulence. A flame flickers not because it's struggling to stay lit, but because the air around it is swirling unpredictably. Oxygen feeds in from all sides in uneven gusts. Heat rises, creating pressure differences. The result? A living, moving flame that curves and twists like it's got secrets to tell. Want something even more poetic? The galaxies themselves, those majestic, spiral cities of stars, form and evolve in part because of turbulence in the clouds of gas and dust from which stars are born. Turbulence compresses matter, triggers collapse, kicks off fusion. Without turbulence, there might be no stars at all. And in case you thought technology had it under control, nope. Supercomputers can simulate turbulence in small spaces, maybe in a tunnel, maybe in a short pipe, but try to simulate global weather patterns with turbulent systems. That's why your weather app is usually right, but not always. Predicting turbulence over long timescales is like trying to guess the shape of steam. And that's the thing, turbulence isn't disorder. It's unpredictable order. It's motion too complex to look linear, too vast to call random. So when you stir your coffee in the morning, or tonight maybe, in a midnight kitchen with only the hum of the fridge for company, you're witnessing something that baffles science, dances like poetry, and curves like everything else in this unruly universe. That tiny whirl in your cup, it holds the same patterns as a hurricane, as Jupiter's storm, as the primordial clouds that formed stars. Your spoon is just the starting point. You're shrinking now, not in a terrifying Ant-Man way, no ants, no drama, no sudden zoom-ins on dust mites. This is a gentler descent down past skin and bone, past cells and nuclei, down into the microscopic world. Things are soft here, wet, busy, and wiggly. Because down here, at the scale of life's tiniest architects, nothing moves in a straight line, not even close. Let's meet a bacterium. Call it Larry. Larry is about 2 microns long and has a single, spiraling tail called a flagellum. When Larry wants to go somewhere, he spins this tail like a propeller, not with a smooth whoosh, but with a jerky, helical motion. If Larry spins it one way, he tumbles. Another way, he kind of barrels forward. But it's never a straight shot, not even for a moment. At this scale, Larry doesn't just fight friction, he lives in it. He's like a goldfish trying to swim through peanut butter. The physics of his world are completely different from yours. He doesn't glide, he wiggles. And because water feels thicker to him than molasses feels to you, his path looks more like a drunken noodle than a laser beam. You're now deep in the realm of low Reynolds number physics, a world where inertia is basically non-existent. Once something stops moving, it stops. There's no gliding, no coasting, no gentle deceleration. Larry has to flap or spiral or squirm constantly just to stay mobile. And if he wants to turn, it's not just a left or right decision, it's a reconfiguration of his entire body. Microorganisms in general have motion that would make a physicist weep and a modern dancer weep with envy. Amoebas ooze, cilia beat, flagella whip. Some algae use a 2-flagella system that lets them swim in corkscrews. Others flick themselves backward or spin in place until random motion takes them somewhere new. There's very little forward, a whole lot of kind of. Historians, biologists, still argue over whether certain microbes evolved motility out of necessity or as an emergent property of shape and chemistry. But they all agree, straight-line travel is almost never the result. Even bacteria that try to go straight can only do so in short bursts, before tumbling into a new direction. And this isn't just about bacteria. Zoom out a bit, just a little, and you're in the realm of cells. White blood cells. They crawl, not like spiders, more like blobs. They extend pseudopodia, false feet, that grip and pull and contract. Their movement is slow and irregular, more like watching a lava lamp ooze than anything remotely robotic. Yet they track infections with impressive precision, winding through tissues, squeezing through narrow gaps in blood vessel walls, sensing chemical gradients like a tiny detective in a very gooey noir film. And even sperm cells, those supposedly efficient laser-guided torpedoes, don't actually swim in straight lines. Their tails beat asymmetrically, causing them to corkscrew through the fluid. It's efficient, yes, but it's not linear. In fact, the spiraling motion is what gives them thrust and control. Without it, they'd just flail in place. This spiraling isn't accidental, it's foundational. Look at the structure of a flagellum. It's made of microtubules arranged in a circular pattern. The motion it produces is a wave, an S-curve that travels down the length of the tail. That wave creates the spiral. It's a biomechanical necessity. And those microtubules, they're just one part of the cytoskeleton, the internal scaffolding of cells. And guess what? That cytoskeleton is made of curved proteins. Everything in a cell is soft, flexible, bendable. You won't find hard edges or rigid lines, just networks of tubes and filaments and folded membranes, all in a constant state of dynamic adjustment. Even at the molecular level, life curves. Proteins fold into complex 3D shapes, loops, spirals, helices. The alpha helix, a common structural motif in proteins, is literally a spiral staircase made of amino acids. If proteins didn't fold this way, they wouldn't work. Enzymes wouldn't bind. DNA would replicate. Cells would collapse into useless soup. Now step into the cell's transportation system. Tiny molecular motors, like chysin and dynein, carry cargo along tracks called microtubules. You might imagine these tracks as little monorails, guiding cellular packages in neat lines from one part of the cell to another. But again, no. These motors walk, step by molecular step, and their path, while mostly guided, still involves swerves, hesitations, traffic jams, and detours. They don't drive. They waddle, hauling protein-filled vesicles through a crowded, fluid environment. And every step they take, a twitchy, curved motion powered by ATP and pure stubbornness. Want a fringe fact? Some bacteria, like spirochetes, don't have external flagella. Instead, they have endoflagella that run along the inside of their bodies, wrapped like a spring. When they spin, the whole organism corkscrews through fluid. Think of it as swimming by twisting your entire body like a drill. Efficient, yes. Straight, not remotely. Even cell division follows curved choreography. The mitotic spindle, a structure that helps separate chromosomes, forms a rounded, dome-like network of fibers. Chromosomes line up, not in a straight line, but along a gently curved plane. When they separate, they do so in a fan-like motion, arcing toward the poles. And if you zoom in even further, down to the level of individual molecules, they're vibrating, constantly. Quantum mechanics tells us that particles don't have fixed positions or trajectories. Instead, they exist in probability clouds, regions where they're likely to be found. A molecule isn't sitting neatly on a line. It's pulsing through a blurred, curved space of potential. So let's sum it up. At the scale of microscopic life, motion is curved, structure is curved, even behavior is curved. Nothing down here moves like a line. Everything wriggles, everything spirals. Even information inside the cell moves in feedback loops. Chemical signals rise and fall in rhythmic waves, guiding growth, death, healing, and adaptation. You, my friend, are made of curves stacked on curves. Your cells communicate through curved receptors. Your neurons fire in waves. Your entire body is built on the principle that straightness doesn't work. And yet everything functions, not in spite of the wiggle, because of it. So as you drift deeper now, wrapped in this quiet understanding of your own squiggly nature. Maybe you feel a little less pressure to hold things in a straight line, to think in binaries, to move only forward. Life at its smallest scale doesn't do that. It dances. Let your ears take over now. That soft hum you maybe didn't notice until just now could be your fan, or the fridge a room away, or some distant traffic murmuring behind closed windows. Or maybe it's all imagined, your sleepy brain filling in the silence with ambient curve-shaped echoes. Because sound, like everything else in this wriggly universe, does not travel in straight lines. Even in the dark, with your eyes closed and your limbs tucked under blankets, sound curves its way toward you. Here's the thing, sound isn't a thing traveling, it's a wave, a series of pressure fluctuations in air or whatever medium it's moving through. And these waves, though they may look simple in your high school textbook, are anything but linear in the real world. Imagine someone clapping their hands across a quiet field. You, standing at a distance, hear the sound a second later. You might imagine that sound traveled in a nice clean arc from the source to your ear. But if you could trace the actual path, it'd be less like a laser beam and more like a ripple bumping through invisible curtains of temperature, moisture, wind, and terrain. Sound waves curve. This is called refraction, when waves change direction as they pass through layers of varying density. In the air, that means changes in temperature. Warm air carries sound differently than cool air. On a still night, for example, the air near the ground is cooler than the air above. This temperature gradient bends sound downward, allowing you to hear distant trains, voices, or coyotes howling miles away. It's called a temperature inversion, and it bends sound like a magician bending spoons. Historians still argue whether ancient amphitheaters, like those built by the Greeks and Romans, were designed with these sound curves in mind, or if they just got lucky. Either way, the result is remarkable. In the theater of Epidaurus, you can drop a coin on stage and hear it clearly from the top row, over 180 feet away. The curved seating, the stone materials, the slight upward slope, it all collaborates with sound's natural bending to carry your voice like an invisible chariot. Inside buildings, sound ricochets. It bounces off walls, reflects off ceilings, curls around corners. These are called reflections, and together they create reverberation, the equi-tail that lingers after a sound is made. In a small space, those reflections blend into a warm hush. In a cathedral, they swell into something almost divine. But straight lines, not here. Sound also diffracts, which means it bends around obstacles. Ever wonder how you can hear someone talking behind a wall even if you can't see them? Their voice curves around the corner. The lower the frequency, the farther it bends. That's why you can hear the thump of bass from a party long before you hear the lyrics. The low tones bend, slip through cracks, ripple through closed doors. Even in open spaces, sound never travels straight. Wind layers and terrain constantly adjust its path. Forests muffle high frequencies but let low ones roll through. Valleys funnel sound and amplify it. Water surfaces reflect sound upward or downward depending on temperature and wave shape. And underwater, oh, the rules change completely. Sound in water moves faster, over 4 times faster than in air, and it curves dramatically. Whales, for instance, use low-frequency calls that can travel thousands of kilometers underwater, bending with layers of ocean temperature and salinity. There's even something called the deep sound channel, a natural waveguide in the ocean where sound travels incredibly far due to the precise balance of pressure and temperature. Dolphins use echolocation, sending out sound pulses that bounce off objects and return in distorted form. But those pulses don't fly straight like radar. They bend, bounce, refract. Dolphins' brains interpret the delay and shape of the echoes to form a picture of the world, one made entirely of curves. You too echolocate. Not like a bat or a whale maybe, but your brain processes sound spatially. The tiny difference in when a sound reaches your left and right ears, called the interaural time difference, helps you locate its source. But this only works because sound travels in waves that move across your body, bend around your skull, and resonate through the curves of your inner ear. Even the shape of your pinna, that outer ear flap, helps. It's full of ridges and curves that catch sound from different angles, helping your brain understand elevation. You've got little parabolic sound dishes attached to your head, and they work best with sound that knows how to curve. Want a fringe detail? The cocktail party effect, your brain's ability to focus on one voice among many, is partly a function of how your brain predicts the way sound waves bend and bounce around you. You're not just hearing, you're simulating, mapping, filtering. And musicians, they ride the curve. A violin string doesn't just vibrate in a straight pattern. It oscillates in harmonics, multiples of its bass frequency, that create complex curved waveforms. The shape of a trumpet bell, the twist of a French horn, the spiral of a conch shell, they all shape sound by curving its path, lengthening or shortening it to tune a pitch. Even your own voice doesn't travel straight from your throat to the world. It curls through your mouth and sinuses, bounces off your teeth and tongue, resonates in your chest. The shape of your vocal tract bends sound, filters frequencies, forms vowels and consonants like the whisper of a river across rocks. And then there's silence, or what seems like silence. Even in quiet, there's sound moving. Low-frequency ambient hums from traffic, the subtle groan of a building, the movement of air through a vent. You may not hear them consciously, but your ears do. And those sounds, still curving, always. Because even in the dark, even at rest, the world speaks in waves. And waves bend. So tonight, as you lie still, maybe you notice the way sound curls around your room. Maybe the fan in the corner is carrying its whisper across the floor in tiny loops. Maybe your own breathing echoes softly off your pillow, shaped by the hollows of your throat. Nothing moves in a line, not even a sigh. Even your dreams, when they arrive, won't speak to you in sharp notes or clean meters. They'll come in waves, in echoes, in rhythm and resonance. And they'll curve, just like everything else. You thought space was a rebel, thought water and wind had attitude. But time, oh, time makes them all look well-behaved by comparison. Because time, yes, the good old TikTok linearity we pretend to understand, absolutely refuses to walk in a straight line. You're probably used to thinking of time as a one-way street. 1 second follows the next, like train cars clicking forward on a perfectly laid track. Past behind you, future ahead. Forward is progress. Rewind is impossible. Except it's not quite like that. Not at all. Time, like space, bends and warps and stretches. And sometimes, if the universe is feeling especially dramatic, it folds in on itself. Let's start small. You're probably aware that time feels different depending on the moment. A boring meeting crawls. A sunset blinks past in a flash. An hour spent waiting in line can feel longer than a day spent laughing with a friend. Your perception of time is wobbly, subjective, constantly shaped by attention, emotion, and context. This isn't just psychological. Your brain encodes time nonlinearly. It stretches and compresses experience. High adrenaline events like near-miss car crashes or sudden surprises get stamped with extra attention and more detailed memory encoding, which makes them feel longer. Conversely, repetition collapses time. That commute you do every day, your brain compresses it. You remember the highlights, forget the details, and poof, it felt like 5 minutes. But let's zoom out, way out. In Einstein's universe, time is not some sacred constant. It's part of spacetime, a fabric that stretches and bends depending on speed and gravity. You've heard the phrase, time is relative. That's not philosophy, that's physics. Move faster and time moves slower for you. It's called time dilation, and it's been tested, measured, proven. Astronauts on the International Space Station age just slightly slower than the people on Earth. It's a tiny difference, fractions of a second over months, but it's real. Now imagine someone flying close to the speed of light. Their clock ticks slower and slower compared to yours. In theory, if they kept flying long enough and fast enough, they could return to Earth to find that decades have passed while they've only aged a few months. Straight path through time? Forget it. It's more like a maze with adjustable walls. Historians still argue whether Einstein fully grasped the philosophical implications of time dilation when he first proposed it. Some say he saw time symmetry from the start. Others believe the emotional consequences, the idea of twins aging apart, lovers separated by velocity, emerged more slowly. Either way, relativity cracked time wide open. And gravity, as you learned back in Section 5, also bends time. The stronger the gravity, the slower time passes. Stand on top of a mountain, and time runs slightly faster than it does at sea level. Move near a black hole, and time stretches so dramatically that an hour near its edge could equal years elsewhere. This is more than theory. It's been confirmed by atomic clocks placed at different altitudes, and it's the reason GPS satellites need constant time corrections. Without accounting for gravity's effect on time, your phone would direct you to drive into a lake. Straightness doesn't live here. Time bends wherever mass or speed demand it. Want to get even stranger? There's a concept called closed time-like curves, theoretical paths through spacetime that loop back on themselves. If such curves exist, and some solutions in general relativity suggest they could, then time could, under extreme conditions, loop. You could, mathematically speaking, return to an earlier moment. Fringe detail. Some models involving wormholes suggest that if one end of a wormhole is moved at near light speed, then brought back, the two ends would experience time differently, creating a potential shortcut not just through space, but through time itself. Time travel, with all the paradoxes and headaches that entails. Don't worry, no DeLoreans needed. These are just models. We haven't bent time that hard yet. But even without black holes or wormholes, time feels curved. Think of memory. Your life didn't happen in a clean, continuous timeline. You remember it in loops and fragments. A smell pulls you back to childhood. A song sends you to a breakup. You're brushing your teeth in 2025 and suddenly, for no reason at all, you're standing in your grandma's kitchen in fuzzy socks and it's 1998. That's not nostalgia. That's your hippocampus throwing a curveball. Your memories are nonlinear. They loop. They overlap. Some feel closer than they are. Some fade entirely. And the more emotional a moment, the more distorted its timestamp becomes. Even dreams distort time. You might spend an hour in a dream world only to wake and find 2 minutes have passed, or vice versa. Time inside dreams doesn't flow forward, it flows around. And language, we don't talk about time in straight lines either. We circle back to ideas. We look forward and look back, but we also relive, revisit, rewind. We talk about the ebb and flow of time, the passing of moments as if they were drifting leaves, not ticking numbers. Music plays with time constantly. A rubato piano line bends tempo. A jazz solo dances around the beat. Even in structured time signatures, musicians pull, push, drag, and accelerate. It's not just rhythm, it's time bending for emotion. And now consider aging. Your childhood felt endless. Summers stretched forever, but the older you get, the faster years seem to pass. Why? One theory suggests it's all about proportions. At 5 years old, a year is 20% of your life. At 50, it's 2%. The longer you live, the shorter each year feels by comparison. It's a curve, one you feel even if you can't measure it. And then there's entropy, the great arrow of time. In physics, the second law of thermodynamics states that entropy, the measure of disorder, always increases. Systems naturally go from order to chaos. That's why you can't uncrack an egg, why a shattered glass won't reassemble itself, why the future feels open and the past feels fixed. But even this arrow of time, so often presented as a strict forward march, is part of a bigger cycle. Stars burn out, matter disperses, New stars form, galaxies collide, then settle. Even the universe's heat death, if that's where we're heading, isn't a line. It's a drift, a gentle slope into silence. So here you are, curled up at the edge of the clock, feeling time pass not as a straight thread, but as a wave. You don't live in the tick-tock. You live in the rhythm, the pull, the breath. You wake and sleep in cycles. Your heart beats in loops. The seasons return. The sun rises not in a straight path, but in a graceful arc across a turning sky. Time doesn't walk a line. It sways. And you've always known that. You've felt it in the way your thoughts return to old joys, in the way grief rises like a tide, in the strange, sweet ache of déjà vu. Time curves. So let it. It's late now, or early, depending how you like to define the hours when silence folds over itself and time seems to stretch sideways. Your thoughts are slower, softer, but somewhere in some brightly lit room or humming server farm, a machine is still thinking. Not dreaming thinking. Crunching numbers, simulating worlds, drawing pixels, mapping probabilities. And here's the irony, even it prefers curves. Because for all our obsession with straight lines, rulers, grids, spreadsheets, it turns out that curves are computationally cheaper. Nature figured this out billions of years ago, and now, so have our machines. Let's start with one of the most familiar visual illusions of our time, the computer-generated image. Whether it's a Pixar film, a video game, or a simulated black hole bending light in some sci-fi epic, those smooth, natural motions you see aren't built on straight lines. They're built on splines. A spline is a kind of mathematical curve, flexible, adjustable, infinitely refinable. Instead of plotting every single point on a path, you define a few control points, and the spline smoothly interpolates the curve between them. It's efficient, elegant, and weirdly poetic. Computers don't draw lines. They suggest motion and let the curve fill in the blanks. And when you're animating something, say, a bouncing ball or a blinking robot or a sad raccoon with suspiciously human eyes, you don't move it from it to be in a straight line. That would look robotic, dead. Instead, you use easing curves, mathematical functions that describe how an object accelerates and decelerates over time. Start slow, speed up, ease out, a curve. Always a curve. Even video games built on polygons and vertices and code simulate motion using curves beneath the hood. Want to fake a walk cycle? You'll use arcs. Want to simulate gravity? Curved trajectories. Want to blend animation smoothly from one action to another? Interpolation curves. Historians still argue whether early computer graphics pioneers like Ivan Sutherland and Bezier, of Bezier curve fame, anticipated how vital curvature would be to modern computing. But whether they knew it or not, their innovations made it possible to render smooth motion with minimal data. Curves are just more efficient. It's not just graphics. In machine learning, curved solutions show up constantly. Neural networks don't draw hard boundaries between categories. They form nonlinear decision boundaries, wiggly, twisty separations in high-dimensional space. When a model learns to tell the difference between cats and dogs, or fraud and not fraud, it doesn't draw a straight line. It warps and bends a surface through data points, finding the best contour that separates classes. Because real data is never linear, real life is messy, curvy. Even sound, when digitized, is captured in waveform curves, those familiar undulating lines you've seen in audio software. The shape of the wave defines the sound, and when you compress it for a podcast or a phone call or your favorite sleepy science video, the algorithms don't preserve every point. They model the curve, simplify it, and discard what you won't notice. Same with video compression, same with 3D modeling, same with digital art brushes. Every curve is a lie that your brain happily accepts because it looks and feels more real than the jagged truth. Now look at robotics. You might expect a robot arm to move in precise straight lines, but guess what? That's inefficient and unnatural. Human arms move in curved joint space, using arcs and loops to conserve energy and minimize strain. So roboticists teach machines to mimic that, to curve their way through motion, to blend angles smoothly, not just because it looks better, but because it works better. Your own arm, when you reach for something, traces a curve without you thinking about it. Every joint rotates, every muscle adjusts. Straightness would be exhausting. The curve is graceful, economical, smart. Want a fringe detail? The field of computational geometry, used in everything from route optimization to 3D printing, relies heavily on curved algorithms. Even a task as simple as find the shortest path through this map often returns nonlinear answers. The shortest distance between two buildings might look like a line, but walk it, and you'll find curves that save time. Elevation changes, slopes, shortcuts that only make sense when you account for terrain. Your GPS knows this, so does your vacuum robot. But maybe the most poetic example of curves in computation is computer vision. When a machine tries to recognize objects in images, like faces or traffic signs, it doesn't look for straight lines. It looks for edges, gradients, contours. Curved surfaces reflect light in distinctive ways. Straight-edged objects are rare. Most of what you see, eyes, mouths, trees, clouds, is curved. So the machine learns to detect arcs, patterns, probabilities. It doesn't see a cat because it drew a rectangle around it. It sees a cat because of soft shapes, texture gradients, shadows curving around fur. Even your own phone's facial recognition relies on curvature. It maps your face in 3D, identifying the gentle slope of your cheekbones, the arc of your brow, the shape of your chin. A straight face would be harder to recognize. Good thing yours isn't. Even emotions get processed in curves. Sentiment analysis tools used to detect emotion in text don't assign feelings based on direct keywords. They use complex nonlinear models that weigh context, phrasing, punctuation. Sarcasm, that's a sharp curve. Melancholy, a slow descent. Joy, a sudden peak. None of it works on straight logic. It curves through language, intuition, nuance. You're living in a world of machines, and the machines have learned to love the curve. Not because they're poetic, because they're practical. Because curves compress better, render faster, learn more efficiently, move more naturally, communicate more clearly. Even fonts, the very letters you're reading with your sleepy eyes, are stored as vector curves, not pixels. That's how your screen displays a lowercase g in 11 point or 144 point with perfect crispness. It's all math, all curves. So here's the final irony. The machines we built to simulate our world, the processors, the renderers, the pattern detectors, eventually discovered what nature knew all along. Straight lines are wasteful. Curves are where the magic is. So whether it's a baby face rendered in Blender, a drone flight path curving over hills, a tweet analyzed for emotional tone, or a robot arm making you coffee, the machines are bending. Just like the rivers, just like your spine, just like time. And maybe, just maybe, that means you can bend too. Because if the cold, logical world of computation can learn to trust the curve, then the rest of us, sleepy, spiraled, soft as we are, might already be ahead of the game. So here we are, not quite at the end, but close enough that the world is starting to quiet. You followed every bend and spiral, every loop and curve, from the sweat of bacteria to the swirl of galaxies. From rivers to roads, lightning bolts to dream states, you felt the slow unfurling truth that nature doesn't do straight lines, not because it can't, but because it doesn't need to. And now you're wondering something dangerous, something honest. Were straight lines ever real at all? Let's trace the thought. When you were little, you learned to draw a straight line by gripping a ruler, lining up the edge, and dragging your pencil stiffly across the page. It felt satisfying, confident. That line was clean, unambiguous. You called it straight, and no one questioned it. But zoom in. Microscope close. That line on the page, it's jagged. Tiny flecks of graphite, paper fibers torn and realigned, the pressure of your hand shifting ever so slightly with each tremor. It's not perfect. It never was. Zoom further in beyond your pencil line into atoms. What does straight mean at that scale? At the quantum level, particles don't even have positions in the classical sense. They exist in clouds of probability. Your line is now a fog, a shimmering guess. Keep zooming. Into pure geometry, into math. Even there, the concept of a line is an abstraction, an ideal. A line is defined as a one-dimensional object extending infinitely in both directions, with no width, no curve, no end. Sounds lovely, but it doesn't exist. Not here, not anywhere. Not in your body, not in space, not in time. It's a model. A tool we invented to describe things we only partially understand, like north or zero or normal. Useful, but not real in the sense that a breeze or a bruise or a blueberry is real. Historians still argue whether early mathematicians believed that ideal shapes described the world as it was, or just gave them a language to tame the chaos. Plato thought the world of perfect forms was more real than physical objects. Euclid gave us theorems and proofs that assumed flat planes and eternal lines, but even he probably knew they were approximations, maps, not the territory. And look at what we've done with them. We built cities on grids. We mapped the stars with celestial coordinates. We assigned and why to every problem we didn't know how to solve. Straight lines are comforting. They suggest order, predictability. Start here, end there, connect the dots. But that's not how anything truly works. Your life, it didn't go in a straight line. You've looped, paused, backtracked, jumped timelines entirely. You've tried plans A through G and ended up somewhere between improvised and accidentally perfect. That job you didn't get, the person you met at the wrong time, the dream you outgrew, those weren't detours. They were the road. Even your thoughts right now, curling in on themselves, remembering old sections of this story, reframing your sense of motion, that's not distraction, that's structure. Because our minds, like our bodies, like our rivers and galaxies, are not made to move linearly. They spiral. They re-enter. They twist and return and shift course not in failure, but in response. Straight lines in the end are a kind of fantasy, a wish that the world could be simpler than it is, that if we tried hard enough, we could draw a perfect path from birth to brilliance, from question to answer, from now to whatever comes next. But we can't. And that's the beauty of it. Because curves are alive, curves adapt, curves contain surprises. They carry more information than a straight line ever could. They hold elegance, growth, grace. Even the tools we use to measure straightness, levels, rulers, lasers, are only approximations. They rely on context, calibration, the alignment of systems that are themselves flawed in tiny, essential ways. If you drew a straight line from one galaxy to another, it would bend under gravity. It would warp through space-time. It would not remain what it started as. So maybe the question isn't why the universe hates straight lines. Maybe it's why we ever thought it didn't. Because if you look with soft eyes, sleepy eyes, you'll notice it everywhere. The bend of your wrist as you turn a page, the curve of a question forming in your mind, the way this very sentence started somewhere uncertain and now loops back to catch you gently where you are. This isn't an argument against structure, or clarity, or trying to get from A to B. It's just a reminder. If your path feels like a tangle, it's not broken. It's following deeper rules, curved rules, beautiful, natural, very old rules. You are not off track. There is no track. Only motion, only momentum, only you spiraling toward whatever comes next, shaped by a universe that never needed straight lines to begin with.